Any net force causing uniform circular motion is called a centripetal force. The direction of a centripetal force is toward the center of curvature, the same as the direction of centripetal acceleration. According to Newton's second law of motion, the magnitude of centripetal force F sub c is m times a sub c, where a sub c is the centripetal acceleration. Consider the relationship between the centripetal acceleration and the linear velocity and the angular velocity. We get these two expressions for the centripetal force Fc in terms of m, v, omega, and r. It is interesting to notice that if we solve this first expression for r, we get r equals to mv squared over f sub c. This implies that for a given mass and velocity, a large centripetal force causes a small radius of curvature, that is, a tight curve. Let's look at this example together. For question A, because we know the car's velocity, 25.0 meters per second, and the car's mass, and the radius of the curve, we use the equation F sub c equals to mv squared over r to calculate the centripetal force. For the question B, this figure shows the forces acting on the car on a level ground curve. Friction is to the left, keeping the car from slipping, and because it is the only horizontal force acting on the car, the friction is the centripetal force in this case. We use the maximum static friction because in the horizontal direction the tires roll but do not slip. Now we have a relation between the centripetal force and the coefficient of friction. We combine this equation with this expression of F sub c, we get mv squared over r equals to mu s times mg. So for the coefficient mu s, we have mu s equals to v squared over rg, which equals to 0.13. We have just learned from the example that for an unbanked curve, since the friction is the only horizontal force acted on the car, it is the same as the centripetal force. However, for a banked curve, the normal force N and the weight of the car W are no longer along the same line, and these two forces can give a net force which is in the horizontal direction. For a case called ideal banking, the net external force causes the horizontal centripetal force in the absence of friction. Since there is no friction, in the vertical direction we have n cosine theta equals to mg, and in the horizontal direction we have and sine theta is the centripetal force equals to mv squared over r. Combining these two equations to eliminate n and get an expression for theta, we have theta equals to arctangent v squared over rg for ideally banked curve without any friction. Please note that theta does not depend on the mass of the vehicle, and in real cases, friction helps because it allows you to take the curve at a greater or lower speed than if the curve is frictionless. In Chapter 4, we have talked about the inertial frame of reference, real forces, and fictitious forces. We know that unreal or fictitious forces arise from motion and may seem real because the observer's frame of reference is accelerating or rotating. A common experience occurs when a car makes a tight turn, say to the right. The car driver feels herself forced to the left relative to the car when she makes a right turn. This is a fictitious force arising from the use of the car as a frame of reference. In the Earth frame of reference, the driver moves in a straight line, obeying Newton's first law, and the car moves to the right. There is no real force to the left on the driver relative to Earth. There is a real force to the right on the car to make it turn. The car is a long inertial frame of reference because it is accelerated to the side. The force to the left sensed by the car passengers is a fictitious force having no physical origin. The same case applies to the merry-go-round. A rider on a merry-go-round feels as if he is being thrown off. This fictitious force is called the centrifugal force, and it seems that one must hang on tightly to counteract this centrifugal force. In an inertial frame of reference like the Earth, and according to Newton's law, it is the rider's inertia that carries him off. A real force, the centripetal force, is needed to cause a circular path. Otherwise, the rider would go in a straight line right off the merry-go-round. Let us now consider what happens if something moves in a frame of reference that rotates. For example, if you slide a ball directly away from the center of the merry-go-round and assuming the friction is negligible, the ball would follow a straight path relative to Earth due to Newton's first law. But in the merry-go-round's frame of reference, the ball follows a path curved to the right on the merry-go-round surface. We explain this apparent curve to the right by using a fictitious force called the Coriolis force. Because according to Newton's laws, there must be a force that causes the ball to curve to the right. The fictitious force, Coriolis force, can be used in any frame of reference that rotates with respect to an inertial frame, like the Earth, to explain why objects follow curved paths. This allows us to apply Newton's laws in non-inertial frames of reference. And it has a lot of application, including the Earth weather systems. You can read the textbook for more information if you are interested.